加一个对齐，数学口一个老师占多少分？没有，一个老师占20。真的，一会儿占20分。啊？不是那个走吧。哦，不对，那一个考试，哦，那一个那是这个考试加一个翻了好久。是啊，F3一般来说是它不止4个就是那个是4个10分。哦，4个一个10分，10分的小本，然后2格的那个，哦，一次考试扣1分，次考试4分，你要保证期末扣6。
Okay, so back. So first of all, before I start, does anybody have any questions for me? Good. So basically, other than the Java collections framework, thus far what we've studied are implementations of lists, and they sort of fell into 2 categories. Array-based lists are the first things we started studying, and the sort of general statement that you might make about them is that when you have an array-based list, it's fast to get any element because it's just some array index calculation. Typically, even the fancier ones like Rubik's array stacks, it's maybe 2 index calculations, but it's still a constant time operation to get to any element in the list. Doesn't matter if it's near the beginning, near the end, or in the middle. But in all of them, it was slow to add or remove elements in the middle. And that's because for all of them, adding in the middle means shifting a lot of stuff inside the array to move it out of the array. And so that's sort of the general thing. You can get anywhere quickly, but it's hard to add and remove things through the middle. And linked lists are sort of the opposite. With a linked list, you can only start at the ends, and to get anywhere, you have to sort of start at one of the ends and walk through the list to get there. So in particular, if you're trying to get to the middle, that takes a long time. You have to walk over half the elements to get there. But then once you're there, it's actually trivial to add and remove things. So you can add and remove anywhere in constant time if you already have a pointer to the place that you want to add or remove. And so these 2 things are sort of dual this way. And then we've seen sort of things that try and mix the 2, like these space-efficient lists, which is basically a linked list full of arrays. And there's some kind of trade-off where the bigger you make the arrays, the faster it is to get to any element, but then the more time it takes to insert something in one of these elements because you have to shift everything in one of these arrays. So there's a trade-off there, and there's a balance somewhere around the size of the arrays, around the square root of n, then both of these things take about the same amount of time. So today we're going to look at, we're in for a real treat, we're going to look at a very beautiful, beautiful data structure called a Skiplists. And I don't think you guys, many of you who were not even born when these things were invented, to think that this is, recent history. But in terms of, basic data structures, 1990 is pretty recent history. So this things we've been talking about so far, they were, more or less invented in the 1950s. There's a few variations, some fancier variations that came a little bit later. But for someone to come up with something really interesting and new like this in 1990 was a big thing. So Skiplists are this really clever idea of making a list, and it has many applications. We'll see that we can use it if we want to store a set of sorted numbers. We'll see we can also use it if we want to implement the list interface. So we can implement the sorted set interface or the list interface using a skip list. And the idea is that there's a very good balance between the time it takes to get somewhere and the time it takes to add something. Both of these things are very, very fast. So what does it mean to be very, very fast? Basically, we can get to any element in O of log n time. And we can, once we're there, we can add, or the additional cost of adding or removing or finding an element in constant. So that's way better than we can do, even with these trade-offs with linked lists. Log n is much less than the square root of n. Just a few examples. If n is, let's say, 100, square root of n is 10. Log n is about 7. If n is, let's say, a million, square root of n is about 1,000, and log n is about 20. And similarly, if n is 1,000 billion, square root of n is about 1 million, and log n is about 40. So if you're comparing these things, a running time of square root of n, sure, it's much better than n, but log n is way, way better. So this log n running time is the kind of thing we shoot for. Anytime we can't get constant time, we'll log n is usually the next best thing. Okay. So maybe the best way to describe this is to just tell you one way to make a skip list, and then we'll see the different ways of using it. So one thing I should stop and point out is that there's one catch to all of this. So other good things, skip lists are fairly simple to implement. But the catch is that skip lists rely on randomization. So that means the way that they achieve these running times, this fast running log n running time to get to any element, is by using some random choices internally. And those random choices give you this running time, but only in expectation. So this is only expected running. So how many of you are taking I think it's 2804, the discrete structures course, the second one. Yeah. Okay. So there you will learn exactly what all these things mean. Have you done any probability in that course yet? So you'll actually study Skiplists there again once you've seen all the formal definitions. We'll still analyze them more or less formally today, but by the time you take 2804, you'll really get to understand exactly what happens. So these things rely on randomization, which means that these running time guarantees, they're somehow on average over these random choices. All right. So here's how you make a skiplists. You start with a linked list. Singly linked is probably the easiest way to start. Put your values in it, whatever you want to store. Now I'll call these things A, B, C, D, hit E. And I. You start with a singly linked list like this. You add on the front of this thing an empty node, like a dummy, but it's called a sentinel. There's no value stored in it, but it does have a pointer to the first element in your list. And for reasons that will become clear soon enough, you call this list list0, L0. And now walk through this list, starting at this first node, the one that comes after the sentinel, and toss a coin. If that coin comes up heads, then you take this thing and you'll promote it up into another list, L1, that we're going to build on top of this one. If that coin comes up tails, then you just leave it where it is. So let's say we got to this thing, and we tossed our coin, and the coin came up heads, so this guy gets promoted. He's going to take part in this next list that we'll call L1. And maybe this guy came up tails, so he stays here. Maybe this one comes up heads. Maybe this one also comes up heads. And then maybe we get a tails, tails, and maybe another head. The sentinel always gets promoted. And now you make a list of these guys that got promoted. So when I say toss a coin here, coin is not usually part of a computer. What happens inside a computer that's running this is it gets random bits from somewhere, either from a pseudo-random number generator, maybe from hardware, or maybe it has a list of random bits that it's downloaded from somewhere. Any of those things will usually work. And so this thing gets promoted this way. So if you had to guess, on average, how many elements do you think will be in L1? If there's n elements in L0, how many do you think on average would be in L1? Yep. Half the elements. So on average, we would think that L1 has about half the elements. Now, we continue this way. L1 in this case is not empty, which means we can do the same thing again on L1 to make a new list L2. So we walk through the elements in L1, here's the first one. We toss a coin, the coin comes up heads, then we promote the element to L2, otherwise we just leave it there and forget about it forever. So maybe this comes up tails, so we leave it there. Maybe this comes up heads, so we promote it. Maybe this comes up heads, so we promote it. And maybe this comes up tails, so we leave it there. So then that gives us And in particular, L2 is not empty, so we do it again. We get a list L3, and maybe this time, this is tails, so it doesn't get promoted. This is heads. So it comes out, it's the only thing that got promoted. Sentinel. And again, this is not empty, so we do it again. And then maybe finally this comes up tails, and so this doesn't get promoted. There's nothing else in the list, so this L4 is empty, so we're done. That's the way to think of building a skip list, is you start with a list at the bottom that really has the stuff you want to store, and then on top of it, you build these other lists where each one is determined by a sequence of point values. Yeah? Yeah. So each one will point to the next element in the list, and for the last one, that means it'll be set to null. So that's why this one turns to null at this point. There's nothing after it.
Yeah, and for L4, when there's nothing in the list,
yeah.
that means the sentence is also not getting promoted?
You can do it either way. Just the sentence will be null. Yeah.
If nothing's promoted until like list 3 or something like that, do you put nulls below it, or does anything go below it?
Well, if you walk through list 0 and nothing gets promoted, then that's it. List 0 is the only list you have.
What if one thing is promoted, list 1, does anything go below, like any null blocks, or you have it?
How do you mean?
Let's say for list 4, the only thing that's promoted is B. Anything below that, or is it just a straight line B?
Let's see. So you mean list 4?
Yeah.
So list 3 only had D in it.
Yeah, but there's things below it. So for list D,
Yeah.
is there anything below it? You know what I mean?
Actually, not really.
So for list 4, let's see if list 4 would be just draw the box to it with nothing below it. You can draw like that.
Well, I mean, so whether or not this thing ends up in list 4, it's the only candidate to go in list 4, and that's determined by a coin toss. So if the coin toss comes up heads, then D will go up into list 4, and the sentinel will point to it, and then we'll do the same experiment again. So I mean, if the coin tosses come up in straight ways, you can end up with a giant tower. But for now, let's pretend that coin toss came up tails, so we've got nothing in this except the sentinel. And don't think of the sentinel as being part of the list. When I talk about the size of the list, I mean all the number of nodes in the list except for the sentinel. The same way we don't think of the dummy as being part of a double list when we're counting the size. All right. Good. Any questions about that? Yeah. In L3, no, D is still, I mean, the value stored in that node is D, but its next pointer is null. So if I wanted to draw this more explicitly, each of these would be a pair of boxes, and this would be D, 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 D. But actually, the way it ends up being implemented is this thing has stored one data value in an array for all the next pointers. So this is closer to the way it's really implemented. Logically, you can think of it as this is a node that has D, this is a node that has D, this is a node that has D. That's a node that has D. Yes?
Just to clarify that those pointers are pointing to
Yeah, so they would all be really pointing down here. So this thing, this blob here is one single node, and there's 4 things pointing to it. But that looks like it would be dropped down. Okay. All right. So that's what this thing looks like. And one thing that I'll just note now, because we'll use this back later, is we could have done this another way. The first thing we did was we walk through with 0 making L1, and then we walk through L1 making L2, we walk through L2 making L3, and so on. But another way to think of it, which would be exactly equivalent, is we take this node and we toss coins and count how many times those coins come up heads before the first tails. And that would tell us how many lists that this thing will be in. Right? Because tossing coins doesn't really matter what order we toss a coin in. There's no relation between one coin toss and the other. So, so you could say, here what happened is I tossed a coin, it came up heads once, and I tossed it again, and then it came up tails. And here what happened is I tossed the coin, it came up tails the first time. Here it came up heads once, heads twice, and then the third toss was tails, and so on. You get exactly the same kind of list. The technical term for that is you would get the same distribution over lists, whether you did the coin tossing this way or the other way. All right. So there is this thing, this notion of a search path in a skip list. And it's a sort of greedy strategy that start at the highest sentinel. So that is L4 here, the sentinel in L4. And what we're trying to find is a search path for a specific, or we're trying to find a specific node in the bottom list. Let's call it X. So this is the search path for X. So it starts up at the sentinel. And if we can go right, or right literally means right in this picture here, without reaching or overshooting X, then we go right. Otherwise, we go down one level into the list below. Right? So let's say this is X, and we want to know what its search path is. We start out at the highest sentinel node, and we say, can we go right without reaching or overshooting X? Well, here we can't go right at all. There's no way to go right. Or to think of that, another way to think of that is, if we went right, we would go shooting off to infinity here, off the null point or wherever that thing is. So let's not do that. Let's go down. Here, the question is, can we go right without reaching or overshooting X? So can we? We'll actually reach X if we go right here. We don't want that. So we won't do that. So we'll go down. So we don't even want to reach X. Now we ask the same question again. Can we go right without reaching or overshooting X? Yes. Because if we go right, we'll get to this node that has a C in it, and it comes with 4X, so we didn't overshoot it, so we didn't get to X. And now, we ask the same question again. Can we go right without reaching or overshooting X? The answer is no. If we go right, we're going to get to X. We go down. Again, if we go right, we're going to get to X. We go down. And again, if we go right, we're going to get to X. So we go down, and the search ends here. The search path ends here. So the search path is actually a path that takes you to the node just before X in this bottom list. It doesn't take you right to X. And that's important, right? Because remember, in a singly linked list, if you want to do something to the node that contains X, you actually need a pointer to the node before it, not the pointer to X in the node itself. That's why we don't want to do something like go right here and straight down, and then what? We want to remove X from stuff because we needed to change these pointers on those. Yeah. 20 you mention that. I wrote a paper about top-down skip lists about 2 months ago. But does anybody ever do it? No, nobody but me. So, I don't recommend that yet. So not quite ready for prime time. Okay, so this is the search path for X. All right. So that's obvious. Any questions about how that works? There. Super easy. Good. So here's a theorem that we're not going to get hung up on proving right now. We'll do that a bit later. But it's useful. This is the expected length search path for X at most 2 log base 2 of n plus 1. So the length of that search path is about 2 times log n plus 1, 2, or 3, or 5. Somewhere around 2 times log n. So in particular, if there is, what did we say, 1,000 billion elements in that bottom list, then the length of the search path is about 80. So that says if you had terabytes worth of elements, then you might have to look at 80 of them before you can find the node that you're looking for. That's not bad. A terabyte takes a while to scan. You have to look through all of them. 80, that's not such a big deal. Okay. All right, so that's the length of the search path. So let's think about this a little bit. What if we wanted to remove X from this list? Yeah, is that it? Probably want to what? I don't want to flip coins again, because once I start flipping coins again, then I may not get exactly the same kind of distribution. Like, this guy, he had his chance, he tossed a coin, he came up tails, he's done. If I go back and toss a coin again, now he's getting like a second chance of getting higher, so he won't look exactly the same as these other guys we just got to try once. Yeah? Yeah, so I want to do something like this. Anything else? Yeah, we want the whole power of X. Oh no, we don't want to take X's power and move it. Again, because F had his chance. He's a loser. He tossed the coin, he lost. He doesn't get to play again. Yep. So basically, X here appears in a whole bunch of lists, right? It appears in the list L0, L1, L2, L3. We want to get him out of all of those lists. Yeah? Yeah. So, for example, here's another guy that points to X. We should send him off in this direction. There's another guy that points to X. We should send him off in this direction. Basically, copy this value, which means we wiped out completely. And nobody had to do nobody got any second chances at their point tosses. Their point tosses that they got at the beginning, they just stuck with those. Now, what if we wanted to, so this sort of said, well, what we do is we search for X until we find it, and then we kind of backtrack and remove these pointers. Is there a better way to do that, maybe all in one shot? So could we have done all of that during the search? Yeah, so during the search here, we kept using this rule that we go right if we can, otherwise we go down. And what does it mean to go right? Or what does it mean that we can go right? Well, we can go right if the thing on our right is not equal to x and it's not further than x. And so basically, every time we go down here, that's because there was something over there to the right. And if that something is x, well, that's our chance to get rid of it. Right? So here we went down. There was nothing over there, so nothing to do. But here we went down, and the reason we went down is because when we looked to the right, we saw the node containing x. So that's our chance to remove it from the list. And now here we went right, and here we went down, and the reason we went down is because to the right was the node containing x. That was our chance to remove it from this list. And here was the same thing. We went down because the node to the right was containing x. That was our chance to remove it from this list. And then finally, even the same thing is true here. Here we went down because x was to the right. That was our chance to remove it from elsewhere. So in just one search down from starting at the sentinel and searching down, every time you choose not to go to the right because you see x, that's your chance. Just get rid of x from that list at that point. And by the time you get down to the bottom here, x is already gone from all the lists. Yeah. Yeah, so it's the same issue. The same issue as with linked lists. There's a time to remove once you've found the thing, and there's a time to remove. There's a time to find the thing. So basically, here, if you think about this for a bit, there's going to be a while that we follow this search path, and the thing to the right is not x. It's something beyond. And then we reach the first of the highest list that contains x. And from that point onwards, everything to the right is the thing is going to be x. That's the reason we keep going to the right. We keep seeing x. And if you think about that for a bit, well, how many lists are there do you expect there to be like that? Actually, you only expect x to be in 2 of those lists. So the length of the search path is order log n. But the number of changes that you make, the extra time it takes to remove x from that search path is only about 2 lines. So it's sort of, the truth is, I mean, if somebody can tell you where x is, and this thing was linked properly, then you could remove it just by walking back up and doing this, but the hard part is fine. All right. So that's if you want to remove x. So that's it, x is gone. And now, so that's how we remove from a skip list. You just search for it, and every time you see it to the right, you wipe it out of the current list, and by the time you get to the bottom, it's already gone. Now, what if I wanted to add something? And it will be a bit vague about this for now, but let's say I wanted to add it between C and F. So how would I do that? Let's say I want to add, I'll call it X again, so put X back in. Yeah. Okay, so we won't know how we know this exactly. I will draw sort of a magic line here for now. That says where we like to add this new thing that we want to add between C and L. And so we'll search for it. And the search algorithm is the same. Basically, if we can go to the right without going past that magic line, then we'll go to the right, and if we can't, we'll go down. So the search path would be, here we can't go to the right, so we go down. Here we can't go to the right, so we go down. Here we can go to the right. Here we can't go to the right, so we go down. But here that would take us too far, and then here it would also take us too far, so we go. So we can follow a search path this way, even for something that's not in the list, as long as someone tells us, you know, does this thing go too far, farther than we want it to go. And we'll see when we look at the applications of Skiplists what it is that would tell us that. How would we insert something during this? Yeah. Yeah. Exactly. So before we start, we make a new node that contains the thing we want to insert. So let's say we make this new node that contains X. And now, again, before we do anything else, we start tossing points for this node. And they come up heads a certain number of times, and then the first tail comes and we stop. So for every head, we add X, we have another pointer available for X. So maybe this is a simple one. We got heads on the first point toss and then tails the next point toss. And now we're ready to do our insertion. So that tells us that we figured out how high X is. So we know that X is going to be in list 0 and in list L1, but not in any of the other lists. Now, we start following the search path, and every time it goes down, well, we look and see which list we're leaving. In this case, we're leaving L4, and we know that X is not actually going to show up until we get down to L1, so there's nothing to do here when we go down. And the same thing here. We're leaving L3 when we go down, so we don't have to worry about adding X because it's not going to show up until we get to L1. And similarly, when we're at L2 here, we just go down without worrying about it. But here, when we go down to L1, that's because this pointer overshoots X, which means at this point, this is where X should be. It's now time to fix this pointer so that it points to X instead of pointing past X. So then we do two things. We take this pointer and have it point to X, and we take X's pointer here and make it point to whatever this thing is. So now X points to Y in this list. And then it's safe to go down. Now X actually is in the right place in L1. Now we go down to L0. Again, if we went right, we would overshoot wherever we want to put X. And so it's time to, before going down, it's time to insert X by setting this pointer to X. Setting X's pointer. And what that pointer is. And now X is inserted. Yeah.
What do you know where overshoots X?
Well, we'll see that depends on the application. And so the first thing I'll show you is how to implement a sorted set this way, and then it's sort of obvious. Okay, but supposing you know whether it overshoots X or not for now, then is this clear? Yeah.
If X had more X or list, would we have to recreate? You said they were ways.
Yes, the sentinel would have to get higher. And there's a few, I mean, you can totally recreate the sentinel there. That's a fair strategy. You could even double the size to do the same trick that we've used before of doubling the sentinel's array. That also pretty infrequent. Basically, the way to think of it is you basically have to double the number of elements in L0 before one of those guys will percolate up higher than this on average. Okay. All right. So we have this theorem about the expected length of the search path that says it's 2 log n plus O of 1. And we saw that adding and removing, basically all they are is a walk down the search path with a little bit of extra work at a couple of the nodes on the path. And so this theorem translates into, we can add or remove at any position in L0 in the time it takes us to walk along the search path, which is only order long. All right. So application 1 is use this to implement sorted set. Well, that's actually pretty obvious how you do this. The list L0 is going to contain all the elements we're trying to store in a sorted set. So remember, in a sorted set, you want to be able to add 3, 4, 5, 6, 7. And you want to be able to do things like search in the sorted set to find the element or find the element which is comes before the value you're searching for, or the element that comes after the value you're searching for, or if it's there that the value of the element is equal. So for example, if I wanted to search, so let's say this is my skip list. It's supposed to represent a sorted set, so the elements in this bottom list are there in sorted order. And so if I want to search for 2.5, how would I proceed? So what would it mean to find 2.5 in this sort of thing? Yeah, somehow to find it means to say that it comes right before 3 or it comes right after 2. It's not really in itself, but we'd like to be able to say, well, the thing that comes just before is 2 and the thing that comes just after is 2, whichever the user asks for. So how would we do that? Yeah.
Well, ln points to the least element of the intent here.
L what?
L2, for example, is the least element on the second tier.
Yeah, but that.
Top down.
Yeah, so we start at the top and we start looking for 2.5. And we know how to look for something as Skiplists. We can follow this search path. So we start at the top. And if we can go right without overshooting what we're looking for, we do. So here we can't go right at all, so we'll go down. Again, here we can't go right at all, so we'll go down. Here, we look to the right, and we see 3. And this is the node containing 3. We're looking for 2.5, so if we go to the right, we're going to overshoot the element we're looking for. So we don't. We go down. Now, if we look to the right, we see 1. Well, 1 is less than 2.5, so that doesn't overshoot it. We go right. Now, again, we look to the right, and we see 3. That's too far. Down. Now we look to the right, and we see 2. 2 is less than 2.5, so we go right. And now we look to the right, and we see 3. 3 is bigger than 2.5. So this is the stage where we would go down, but we can't. It's the bottom list. And now we conclude that the element that we're looking for is, comes after 2 and is either this element or comes before this element. the search path really is the search path for 2.5. It's how you find 2.5 in the bottom list. Yeah. Well, if we're just searching, if we're just trying to find 2.5, it wouldn't create a new node. It would just tell us 2.5 is immediately before 3 or is immediately after 2. Yeah.
So if you're using a sorted set,
Well, sorted sets do other things too, right? They also include what's called the tail set, the head set, and the subset operation. So this also gives you the tail set because so the tail set is all the stuff that comes after 2.5. So we go to here and we say, where's all the stuff that comes after 2.5? It's actually this list here, starting at 3. So that can give you the tail set that way. And the head set would be this early. So in particular, we can ask for the first element of the tail set easily this way. That would tell us the thing that's on. It will also tell us, I mean, this will also tell us that it doesn't contain 2.5. The closest things are 2 and 3. So sorted sets, the contains operation, it's not, I mean, it's part of a sorted set because sorted sets are special kind of set. But if you're only using the contains operation, you shouldn't be using a sorted set. It's better things to use. Okay, so that's how you find this thing. How about if I wanted to, I don't know, insert 2.5, add 2.5? What would that look like? Same way we added that. We would pick a node for 2.5, make a node for it, pick its height, and insert it the same way we added it. Is that right? Is there one potential issue there? No issues? Yeah. Yeah, so actually, this is a sorted set. A set is supposed to be a collection of distinct elements, so you don't want to insert 2.5 if it's already there. And actually, that is enough to break down this top-down search strategy, this top-down insertion strategy. Because let's say someone asks us to add 3, and we decide we'll add 3, so we create this new node for 3, and we toss coins to see how high it goes, and maybe 3 goes all the way up to level 4. And so now we start our insertion process, which starts to add 3 at level 4, it adds the 3 at level 3, and then we get down to level 2, and we look across and we see, oh geez, 3 is already there. And we started adding a new node that also contains 3, we have to backtrack and get rid of that. The cleanest solution for that is to do a search, and on the way down, use an array to keep pointers to all the nodes where you went down. So that array would contain this thing, contain this thing, it would contain this thing, and this thing. So notice that's exactly one node for each level. So you go down, you do a normal search for the thing you're trying to insert. In this case, let's say it's 2.5. Once you're down at the bottom level here, you know 2.5 is not in the set, and now you insert it, and it's easy to do the insertion now because you have in this array, you have a list of exactly the nodes that you would need down there. So you just insert it the usual way. You put box here, 2.5, figure out how many lists it's going to go into, maybe it's only going into 4 of them, and you use this element, and this element, and this element to update it. So it's a little bit complicated because you're not supposed to store the same element. So adding is about the same with a little bit of complication because you have to be a little bit careful about not storing the same element twice. How about removing an element? Yeah.
I just have a question about storing an element. Why can't you just create the element first, then go and see if it's there, and if it's not there, put it in without having to go through all of it over again?
Well, that would be going through all of it over again. So you put it in. So first you see if it's there. And so that's following the search path. And now you say, okay, it's not there. Now I want to put it in. Well, how do I put it in?
And you just do it like while you're there.
Well, that's basically what you're doing here. But the problem is these linked lists are singly linked. So once you get down to 2, you can't get back to 1, and you can't from 1 you can't get back to the sentinel, and so on. So basically, you're just leaving some breadcrumbs in this array to tell you where are the places that you need to go back to insert this. I mean, the other alternative is it's less efficient is to search for it, make sure it's not there, and once you know it's not there, do the top-down insertion process. But then you're traveling along this search path twice. It really takes twice as long. And the nice thing about this is, again, the search path is fairly long. It's a length log n. But on average, you're actually only inserting this thing in a couple of lists. So that backtracking step is only updating a couple of things. So it doesn't add much to the cost of this. All right, so that's adding. And how about removing? Anything fancy there? Pretty much done already. Well, you don't even have to worry about that because there's no backtracking or anything. You just follow the search path for the element you're removing, and anytime you look to the right and see that element that you're supposed to be removing, you splice it out. If you never see it, well, you never did anything, so that's fine. You didn't remove something that wasn't there. And if it is there, it's only there once, so that's splicing it out. Gets rid of it. So it's basically, it's the original removal element. You look to the right and see what you're trying to remove, then just get rid of it. So that gives us this nice theorem. Skiplists implement sorted set base. And adding an element, removing an element, and searching for an element each take log n expected time. So if you have never done, you've never taken a data structures course where you've seen some kind of sorted set implementation based on a binary search tree, in particular the old school ones, things like red-black trees and so on, you don't appreciate this yet. But this is an incredibly simple data structure, and simple in the sense that I've just explained it to you. And there's a good fraction of you that if you got on a boat or a plane today with your laptop and that plane crashed and you got stuck on a desert island, no internet access, and you really needed to implement a skip list, there's a good fraction of you that would remember everything that you need to do to implement this. these things which have this performance, this O log n times performance bounds, you would not have a chance in hell of remembering exactly all the details of the implementation. So this is a really clean thing. I know this for a fact because we'll see a data structure later in this course called the red-black tree that I have implemented 3 times in my life. Every time I have to go back and look over the details. And I've taught it to students at least 7 times in my life. And before every lecture, I have to go back and look at the details of this. So once we get to red-black trees and we see how they work, we'll be duly impressed by the simplicity of this data. Okay. Here's another neat thing you can do with Skiplists. You can implement lists. Start with a clean picture. No. So you can also use a skip list to implement a list. Not too surprisingly. So again, you have your digits L0, L1, L2, however many you get from these coin tosses. And in the bottom list, L0, well, that's really the list that you're representing. So in the list that you're representing, this is the 0th element, 1th element, 2nd element, 3rd element. And I guess that would mean that the sentinel is the element at position -1. It's not something that the user gets to access, but it's handy to think of it as position -1. And what you do is, for each next pointer you have, you store an additional piece of data, which is called the length of that pointer. So at the bottom level, all of these pointers have length 1. And what the length tells you is, if I follow this next pointer, how many positions in the list do I advance? So here, I go from element at index 0 to element at index 1 by following this pointer, so this one has length 1. This one, on the other hand, takes me from -1 up to 1, so it has length 2. And this one also has length 2 because it does the same thing. And this one has length 2 as well. Okay. So, what are the operations that a list does? Well, in a list, we often want to get the ith element. That's the sort of the most basic thing, extracting the ith element. So let's say here, I want to get, let's say, -2. So I want to quickly get to this node here. And this is a skip list, so you can guess we're going to somehow follow the search path for this node. The question is, do we have enough information to follow the search path for this node? Yep. Yeah. So basically, we know that we start at the sentinel, we're at position -1. And we follow the same rule. If we go to the right without overshooting what we're looking for, then we'll do so. Otherwise, we'll go down. So here, we're at position -1, and we see that there's this pointer here of length 2. And -1 plus 2 is 1. So So we know that this will take us to the node whose index is 1. And that's okay, that's smaller than 2, so we'll do that. Follow this. Now, from this node, there's no option. We can't go to the right, it has to go down. Now, we know we're at the node whose index is 1, because we've been keeping track. We started at -1, we added 2, now we're at index 1. And now we look to the right and see, well, if we follow this edge, we're going to advance 2 positions. So that would take us to 1 plus 2 is 3. That's too far. We don't do that. Go down. And now, we are standing at this node. We still know we're at position 1, because we've been keeping track of this. We look to the right, and we see an edge whose length is 1, and that will take us to position 1 plus 1 is 2. That's exactly where we want to go. So there we found the node we're looking for. So we keep these lengths on the edges as a mechanism to know when we've gone too far. So someone asked that. How do we know, where this magic line is that we're not supposed to go over? In this case, it's by keeping track of how far we've walked, and then knowing the lengths of each edge to know if it will take us too far in that direction. Yeah? Well, for the get, you can go even to reach 1. Yeah. But for remove, we don't want to do that. Yeah. To get it, the first time you see it to the right, you can stop. But on average, that's not going to save you much because on average, these guys only appear at the bottom of the row. So I can find any node in this representation in the time proportional to the length of the search path, so in order log n times. What about adding something? What if I wanted to add something at position 3, let's say? So I want to add at position 3, I want to add the value, the node that contains Q. Yeah. Yeah. But before we do that, what do we do? Before we do that, we make the node and decide how high it's going to go by tossing a point. So we make a node that contains Q. And we decide how high it's going to go. So maybe we got 1 coin toss. We got lucky with the first coin toss, but then the second one came on failed. So it's going to go in L0 and L1. And now we follow the search path for 3, the index 3. And that search path starts over here at -1. It happily goes to position 1. Here it cannot go right. And it's not time to start inserting Q yet because Q doesn't appear on this list yet. Right? It's not big enough, so it goes down. Here we would like to go right, or so we don't want to go right because it's too far, but it's time to start inserting Q. So we want to insert Q. That's easy. That gets us those requirements. But we need to know the length of the, we need to now tell the 2 pointers what the lengths are. How do we do that? So this first edge here, how do we know its length? Yeah?
It's only on
That's not true. So we know at this point, we've been keeping track, we know we're standing at the node whose index is 1. Yeah?
Would you expect the size of the actual list?
No. Something not depends. So here we are standing at the node whose index is 1. Yeah?
Maybe we have
Yeah, just to follow the search path, we need that counter that starts at -1 and then here it goes to 1. So we know we're at the node indexing 1. Yeah.
Now we know that the length between that one and that two is our current position plus the index we're putting to that. And we know that where three is going to make a difference.
Yeah. So the length of this edge is 3, because that's where we're putting this. -1, because that's where we're scattering. So we figured out that the length of this edge is, again, 2. That's a coincidence that it's the same as before. And now we need to know the length of this edge. How do we do that? Yeah.
Now you know our position is
Yeah.
and from that you can
Well, we actually get it from the old length of this edge. So,
oh yeah, so we subtract, yeah.
so imagine that we had put Q in here and this thing still jumped over it. So that would mean that it jumped 3 positions into this array. But now we're splitting this edge in 2. So 2 of them, here's one that's jumping over 2 positions. So this one must jump over the rest, which is just 1 position. So this is an edge of 1. So we get this by taking this number, adding 1 to it, and then subtracting this number here. This 2 here, this 1 all in here, this 2 is not. So you can get the length of the edge. And so now not only do we insert it properly, but we correctly updated the length of the edges, and now we continue following the search path for this thing. So that goes down, that goes right. Here it's about to go down, but of course update these 2 points. And again, we knew we were at node at position 2. We're inserting the node at position 3, which means this pointer must have length 1. And what's the length of this pointer? Well, it used to be of length 1. We add 1, and then we subtract this 1. So this one is also. Because we're in the bottom list, we could have deduced that anyway, but there's no special case needed for the bottom list. It's the same calculation. All right. So that's how you add one of these things. And again, it's just a straight shot down the search path, putting in, splicing in a few things along the way. Removing. What if I want to now go back and remove? Well, let's say give. Yep.
The same thing as we go down, add on to 2, subtract 1.
Yeah. So we just search for this thing, same way we would search for it if we were getting it. That'll lead us through all these nodes in the search path. And sometimes when we look to the right, we'll see the thing we're trying to remove, which means we want to splice it out. So we take these 2 yellow edges, merge them into one white edge, and the length of that white edge is the sum of these 2 lengths minus 1 because something's going with this. And the same thing here is 2 yellow edges of length, each of length 1. We merge them into one edge of length 2 minus 1 is 1 edge. So very clean. I mean, it's really tight with this. It's really nice. I encourage you to look at the book and look at the code. I'm not hiding anything from you. Okay, so that's how you can implement get, how you can implement add at a position, remove at a position, and of course set is the same thing. You find a node and you change the value that's stored there. So that gives us another here. So skip list. His list and implement getting the ith element, setting the ith element, adding an element at position I, and removing the ith element, each take. Now compare that to all of the things that we've looked at before. The other things were horrible, right? Getting the ith element would take like order I time. I could be as big as n over 2. So I could, for n is a million, I could be half a million. And this will do it in something like basically skipping through 40 elements. So 40 versus half a million. That's the kind of the trade-off we're talking about. So very, very well worth doing. Now, all of this, of course, relies on this thing, which we have not proven. This theorem that says, if I follow this search path, then I expect, or on average, I will visit only this many nodes. So let's prove that theorem. But let's start with some easy warm-ups first. Here's a question. And again, many of you have not even learned the basic definitions of probability theory, so we can do this in a sort of not super rigorous way, but in a way that later on after you learn this stuff, you would know how to turn this into a fully rigorous argument. So let's ask, I've already answered it. What is the expected size of L1 if the size of L0 is equal to n? So if there's n elements in L0, what's the expected size of L1? Yeah. Yeah. So you make it into, from L0 into L1, if a coin toss comes up heads. And so coin tosses come up heads half the time with the fair coin. So we expect that half the elements will make it into L1. So the answer, write it this way. The expected size of L1s, so this is the size of L1, the expected value of that is 2. All right, let's change the question. What about the expected size of L2? Half of L1, but I would like to write it as a function of n. Yeah. So let's reason through this carefully. When does a guy from L0 make it into L2? Well, that means this guy tossed a coin and it came up heads, and he tossed another coin and it came up heads. If we look at all the ways you can toss 2 coins, there's 4 different ways that they can happen. You can do heads, 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 tails, tails, heads, or tails, heads. 4 different ways that can happen. And only one of those 4 ways is the one that gets this guy up into the L2. So it's n by 4. So, n by 4. And that's just because out of these options, heads, 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 tails, tails, heads, heads, tails, only heads, heads puts him in L2. And the other thing that's sort of hiding there is each of these outcomes is equally likely for those coin tosses. So only one of us more. All right, let's change the question again and say Li in general. So the general value of I. Yep. N over 2 to the n. right? And only one of those possible ways gets you up to this line. That clear? Good. All right. Next easy question. What is the expected size of all the lists? L0, L1, L2, L3, L4, up to what? We know we only have n lists. Up to L infinity. There's always a chance that we have any number of lists. I mean, there's always a chance that some guy came up and tossed a coin a million times and it came up heads every time, so we end up with a million lists. So it's better to think, we just have an infinite number of lists, there's just a whole bunch of them that are empty. And in fact, we even know that what's the expected size of the millionth list? Well, it's n. When we write it, the expected size of all 1 million is equal to n over 2 to the power of 1 million. Not 0. It actually has some average size. Usually it's 0, but there is a small chance that it could not be 0. All right. And so, what is the expected size of all of this? We have all their sizes. Yep. It's their sum. The expected size of L0, the expected size of L1, the expected size of L2. Well, the expected size of L0, there's no randomness there at all. It's just n. And the expected size of L1, well, we figured that out. That's n over 2. And in general, the expected size of Li is n over 2 to the I. So the answer is n plus n over 2, n over 4, n over 8, 16, and 2, dot, dot, dot. And the condensed way to write that is the sum I 0 to infinity n to the I. What is that sum equal to? If we start adding all of these up, we start with n, then 3n over 2, and then so on. Are we ever going to get to 2n? Not quite, except in the limit. So by the time we get to infinity, which we don't really do, we get to 2n. So this expected size of these things is exactly 2n. All right, so that's